started then. So as you have understood, my name is Charlene. And so first of all,
it seems to work. I do that.
Oh, okay. Okay, so all of our work focus on the HL-LHC next upgrade, which is the high luminosity upgrade, which is aimed to start in 2029. So during this upgrade, we are going to increase the luminosity of the accelerator, which is aimed at also increasing the event complexity. So we get around 200 photon interaction, which is the pilot. And we are also going to increase the data taking rate. Atlas is going also to upgrade the detector, and one of the upgrades consists in installing a new inner tracking detector, which is ITK. So here you see the main challenge of this next upgrade. So here you get the CPU consumption as a function of the year, and you see that at the beginning of the HL-LHC, we got a trouble because the CPU need for Atlas exceed the budget model for it. So we need to find a solution to make these two curves fit. And we do know that one of the really CPU intensive stage of the reconstruction is the track finding part of it. So one thing that we can straightforward think is let's just apply the machine learning techniques to it. But it's not so simple because the raw data from collision are space data. So we have seen in the last Fura and also in the beginning of this workshop that graph neural networks applied very nicely to it. So we all get starting with a proof of principle by the ExaTrack project. And this method and proof of principle were completely extended to the TrackML challenge by L2IT and ExaTrack project. And now we are looking of implementing this method in the Atlas ITK. So here is the pipeline that I'm going to explain in more detail. So the first step of it is to construct the graph. So to construct the graph, the first thing that we need is data and also to define what do we want to reconstruct. So we are going to use a TT bar sample with a pilot 200, and we are going to define what we call our target particles. So we applied a PT cut of 1 GeV. We don't want to reconstruct the secondaries and the electrons for now. And we are asking for at least 3 space points, not cluster. We are looking at space points. So if you look at ITK, it is divided into two subdetectors. So the first one is the strip subdetector. In this subdetector, to create a space point, you need 2 clusters. You get also the pixel subdetector, where to get 1 space point, you just need 1 cluster, which means that if you look in the strip subdetector, you can create some particular kind of space point that I'm going to call the ghost space point. So if you get a particle which travels this way and with a hit there, it's going to fire this strip and this strip, and another one which fire this one and this one, which means that we can have an accidental combination between those strips. This is the ghost here, and it is made of 2 clusters coming from different particles. And you will see later that it is actually a trouble for us. So we are going to build a graph. So in a graph, one node represents 1 space point, and then an edge is just a connection between 2 nodes. So we give a meaning to this edge. This is the probability that the 2 nodes are successive nodes of the same track. So here you get a really simple example with only 19 hits in the ZR plane. But the trouble is that with an ITK, we have 300,000 space points. So if we are going to build a fully connected graph, we end up having 10 to the 10 edges. So this is not the solution, and we are to think of a smarter way to build the graph to remove all the unphysical and also a little bit stupid connection that we can find in that case. So we are designing 2 kinds of solution to create a graph. So the first one is the metric learning one. So in this solution, which is a machine learning solution, you are going to take your track and teach multi-layer perceptrons to embed those space points into a space where they are really close to each other. within a circle of radius R. So the MLP will learn to put all these these nodes in the same circle. The other kind of solution is what we call the module map solution, which is more of a data-driven solution. And we are going to simply learn the possible connection using the simulated sample. So we are going to follow the path of a target particle inside ITK and record all the possible connection. And all the possible connection we are going to be triplets of silicon models. So of course, using this solution, we need a lot of different kind of particles to be able to fully cover all the possibility. So we have built the module map using 90,000 events, which comprise, in that case, 1.2 million connections. And then the second part of it is, well, we are going to use these two methods to build the graph. So if we are going to use the metric learning, we are just going to connect all the nodes which are in the same radius R with central nodes, which means that in that case, you don't get a particular meaning of direction. In the module map case, we are going just to follow the connection which is in the module map. So for instance, in 1 to 3, you get a 3 model here and fully connect all of the modules, which means that in that case, you get a direction inside out, which are given to each one of the edges, which is not the case for the metric learning. And then from the both method, we are going to apply further selection requirements. So additional filtering is done using another multi-layer perceptron for the metric learning and just geometrical cuts within the model maps. So using these two methods, we are able to build graph, and we are targeting the metric learning to build graph which are as big as the one made by the module map. So we are building graph which are around 1.3 million edges. And then, of course, what we do need is high efficiency, because if we lost an edges during the graph construction, it cannot be retrieved later. So which means that the particle on which we have lost the edges cannot be well reconstructed. So this is the efficiency, the graph edge construction efficiency we get for the learning on the module map as a function of eta and as a function of pt. You can see that using both of the methods, we get high efficiency for the graph constructions. And in the next part, we are also only going to consider the module map solution to build the graph. So this means that now we get graph, and we can label each one of the edges. So using a graph neural network. So this is the model of graph neural network we are using. So the input graph is added with features. So the nodes are F, A, Z as the features, and the edges are different on the geometric of the two nodes. And this input graph are given to first stage, which is the encoder state. So we are going to embed both features into an n-dimensional space. And there we are going to apply the core of the graph neural network model, which is the interaction network. And the interaction network is the one which will learn the geometrical patterns of the tracks. So which means that even if we are going to label the edges, what is going to search the GNN is tracks. And we can do that using the message passing. And the message passing will apply this block situation of edge and not block multiple time, L time. And if we do that, we are going to propagate the information to the graph. And then we have the decoding part, which is going to transform the latent features of each edges only. We don't do it for nodes, into a classification score here for each of the edges, which means that now we can have this probability that we want to know if the edges belong to the track or not. So we had to train the GNN and use a configuration for it. So we use only 2 layers in each multi-layer perceptron. We have quite a large number of dimensional space parameters, and we are using 8 message passing, which is enough to propagate all the information inside the graph. To train the GNN, we use 400 graph for training and 20 for validation. And we are using the IMECRAD optimizer, which is a variant of the ADAM optimizer. We are just using the binary cross entropy loss. And this is what we get at the output of the training. when the training is done. So you get the background rejection as a function of the signal efficiency. So you do see that we get a very nice classification from the GNN. And just for illustration here, I put this dot at 0.5, which is the cut on the classification score, but I'm going to show you the result with a little bit more details. So if we are looking at this cut on the classification score with more detail, we can have the efficiency, the per edge efficiency as a function of theta here, of PT here, and the purity only as a function of theta. So you see that we get quite a degradation in the central region. So you can see it here is the efficiency versus theta, but also on the purity versus theta. And this is the same thing for the PT. We get a degradation of IPT because IPT track travel through the central region. So the first thing that we start looking at is where and what does this degradation in the central region occurs. And the answer is it occurs because of this misclassification that we get in the central region. So here you get the RZ per edge purity. And you see that most of the impurity came from the strip barrel regions here. And another thing that we have looked at is what is clearly meaning of this package. What is the origin of all this package? And what we have discovered is that the main, all the first gulfy for the package is this ghost that we get, which is not so surprising because they are really looking like the regular space bond that we want to add. And so the degradation that we see in the central region come from this degradation here, which comes from the lower spatial space bond resolution that you get in this part of the detector, but as well the existence of ghost space bonds. So now that we are understand a little bit more the edge performances, we can look at track, and but we only have here number which are attached to each edges, which is not track. So we have first to build tracks. So to do it, I just draw some sketches to help understand a little bit of the flavor. So here you get a different configuration of what you can see. So of course everything is simplified here. So the first part of our track building candidate is to apply a very low cut on the edge classification score. And this low cut is really like a cleaning cut and help us to reduce the total number of edges. So we, instead of having 1.3 million edges, we had 30,000 edges. And when we are applying this lower cut on the edge classification score, we can see some structure will start to appear in the graph, and all of the structure are going to be disconnected from one another. And this structure has actually the tracks which start to appear. So here I just put some example of what the kind of structure you can find in a graph. And you do see that from some of the structure, we need to apply further selection requirement in order to get the track. So so this means that this further selection requirement is what we call the walkthrough algorithm. So of course, if we get with this kind of track candidates which come from the connecting component, we are not going to do anything. We're very happy it's the perfect case. But it does not happen always. So we are going to apply this walkthrough algorithm, which is basically a set of higher curves on the classification score. And this is going to discriminate and propose track candidates. And at this stage of the pipeline, we are going to ask for a single track assignment. So each space point can only belong to one track. Which means that if we are looking at this kind of structure, you can you have two possibilities, and these two possibilities can completely occur because this algorithm doesn't know anything about physics. It also means that if we get a shared hit here, but at this stage, we have to make a choice, which is none of this different possibility here as a good choice. But for now, this is what we get. And also this kind of really messy track candidates are completely killed during this stage. So now we can look at the track reconstruction efficiency. And so for it, I really want to say that here we does not apply any kind of track fitting. And we are going to study two kinds of matching criteria. So the first one is the standard matching, which is you have to get half of your track candidates which belong to a standard. And the other one is the strict matching, which we also call the perfect matching case, because you doesn't have forget a single hit and you doesn't have had some spurious hit to the track candidate. And this is our final GNN track efficiency. So here is the function of eta, and here are the function of PT. So in black, you get the strict matching, and you can see that we get a quite interesting and really promising results, even before track fitting. And the standard matching is at 1, but this is before track fitting. And this is the same thing for the PT, really interesting and promising results. And we also are starting looking at the fake track rate, but we doesn't have applied yet any kind of track fit. So which means that to define a track, we are just looking at a track candidate which is not matched to any particles, and this is a fake track. And this is fine to be 10 to the -3 before any kind of track. So for the conclusion, we are very happy because this is the first result using the GNN pipeline within ITK, and we get really, really promising results. And of course, there is a lot of work which is still needed. So there are several studies which are ongoing quite at the same time. So we want to finish integration to ACTS and Athena. So I think that for this bullet, you can look at Alina posters. We also want to do a comparison with the Kalman filter, and of course also apply the track fitting. And we are also looking at new GNN architectures to fix the degradation of efficiency in the strips. And Daniel is going to give a talk during the workshop of some of our ideas about this new GNN architecture. This is all for me. Thanks a lot.
Thanks very much for this very clear talk. Which is open to questions. I don't see Zoom is quiet today in the room. Andy.
So it seems to be this the map building or the module map building something the common feature we have seen now in several talks.
Yes.
Has anyone tried here something like self-organizing maps or algorithms as we did in the past with nearest neighborhood libraries that are around there?
Yeah, so no, we doesn't have tried anything else for now. Of course, we know that this is not a final craft construction solution, and the module map needs clearly some work. And we are, I mean, everything can be done at this stage.
Can you update the map? I mean, the more data you start running, the more data you run, you get, the more like you get the edge cases or something. Is that?
If we get more data, we are going to increase the efficiency, which is always good. But it also means that if we see too much data, we're also going to increase the size of the graph. It can be, I think, controlled by using further selection after it. So
There was another question.
Yeah, so like, do you have some sort of a plot of, say, efficiency as a function of threshold? So you showed that the threshold is too low, then you have a lot of fakes. If the threshold is too high, your fakes will reduce, but it would be at the cost of the efficiency, right? Like some true tracks might also lose. So in that case, like, firstly, how do you come up with like an optimal threshold, and like, do you make distributions and then choose the minimum?
So for the threshold we have used to build this result, I just make a very dumb grid search because it's not so easy to find the optimal working point of it. Besides, I don't have at this stage so much time to optimize it. So I'm sure there is a lot of improvement we can be done by using optimal, by choosing the optimal cut, which is clearly not what we are doing now, which is to apply the same cut on all the detector, which is which is something that we shouldn't done.
Like,
But
different regions should get different thresholds.
yes, exactly. Yeah.
Oh.
Are you
Can you, for the purpose of the people on Zoom, just state the name?
yeah, I'm Gage. Are you treating differently the number of times you see an edge when you fill the module map? For example, you might see one edge a lot of the time, and you might want to prioritize that over one that maybe you only saw once.
Yeah, it is a really good question, and no, we are not doing it. We have considered it because obviously, if we get 90,000 events, with each one of the events is a bunch of thousands of particles, and then in the module map you get a connection which only appears once. Do you really want this connection or not? This is, and at some point you can also think, what about the one which appeared twice and third and etc. You can put a cut on this threshold as well. But the difficulty here, but we are dominating by pile-up interaction. And in iClass, we get some pile-up overlay between events, which means that if you just count the number of times the connection appeared, well, sometimes the count can be lower than the really different particles, because it's just the same particles which are going to appear in multiple events. So this will need a really detailed studies, which it's obviously needed, but I think this should be done with really much detail of the module map when we get a module map built with enough events to have the desired.
Any further questions? Yeah.
Yes, Jackson. I guess so. If you're building your module map from like a standard model process like TT-bar, how can you be sure that you're not potentially biasing yourself against more exotic track signatures like long with particle?
Yeah, so we cannot be sure now, but of course in the future we can increase the kind of event of a module map scene to get really all the possible connection, and that can also be done for the GNN training. Like it doesn't have to be trained with only TT-bar events.
I see no more questions, so let's thank the speaker again.